So welcome to SCA's webinar today with Lori Green on mapping faulted surfaces with Petrel. Before we start today's webinar, we'd like to ask a few questions about the demographics of our audience. So I've got some polling questions that I will launch. And the first one is, what is your primary discipline? We have some votes coming in now. Looks like we have quite a few geoscientists in the audience. No surprise, there are a few petroleum engineers in the crowd, but I'd say the vast majority are geoscientists. About 2/3 of you have voted, and looks like we're at 90% geoscientists, 5% petroleum engineers, 5% petrophysicists. So I'm going to go ahead and close the poll and share the results. Heavily weighted towards geoscientists today. And then we have another question. How many years of full-time experience do you have in the oil and gas industry? So again, we're starting to receive your votes. Looks like a great distribution here. Most of you have some experience. With looks like almost 75% of you have voted, and so I'm going to go ahead and close the poll and share those results. 18% are in the 1 to 10 year range, 14% at 11 to 20, 29% 21 to 30 years, and 36% have you over 30 years experience. So we've got one more question, and this is about the topic of today's webinar. So how many years of Petrel experience do you have? Again, we're starting to get some answers now. Looks like, again, we have a pretty wide distribution. So about 80% have voted, so I'll go ahead and close the poll and share the results. We have 29% of you with less than 1 year, 36% are in the 2 to 5 year range, 21% are at 6 to 10 years, and only 14% of you have 10 or more years of Petrel experience. So as we launch today's webinar, I want to remind you that you can use the webinar features to ask questions, to type your questions in throughout the webinar, and we will have those questions and answers at the end of the hour. Again, today is Mapping Faulted Surfaces with Petrel. Lori Green is our instructor, and this class was designed by Lori. She's a senior geologist, and she has quite a bit of experience in working for both operators and service companies using Petrel and other computer systems, and she has a BS from Cornell and an MS from USC Santa Cruz, and she's registered as a professional geoscientist in the state of Texas. So the class that Lori is giving you an excerpt of today is a 4-day course. It's a new course for SCA that gives you more information about how to use Petrel knowledgeably with the right techniques. And this class will be offered as an in-house class. So if you're interested, have your in-house course coordinator contact SCA to see if we can set up the class in-house at your shop. And again, SCA offers consulting, direct hire services. We do projects and studies on subsurface topics, and we also offer training. So at this point, I'm going to give the presenting rights to Lori. And as Lori gets set up to share her information, we will remind everyone that after today's webinar, you'll receive a link to recording, and you'll have a chance to get information about setting up the class. So Lori, let me make sure I've given you presenting rights. Okay.
Okay.
We don't yet see your slides.
Show screen.
Okay, now we see it.
Do you see it now? Okay, all right.
Great. Take it away.
Okay. And my apologies to all. This is my very first webinar. I have taught quite a few classes, but webinar format's a little bit different. So if I hit some bumps in the road, please have some patience with me. But I am very excited about working with SCA. I recently retired, and they've given me an opportunity to share my decades of pet peeves and experience with constructing computer-based maps with a much broader audience than I've had in the past. So definitely thank you for joining us today, and I hope that you will find the 1 hour with us today well worth joining in. So as Susan mentioned, this is just a single topic out of our 4-day class. Mapping faulted surfaces is one of those topics that tends to give people a lot of trouble, and that's partly because the computer-based algorithms are good at constructing surfaces, but they don't really understand that faults need to be handled in a particular way. So I've worked with SCA to extend some of the concepts from their flagship course, the Applied Subsurface Geologic Mapping, and taking those very good concepts into the computer workstation world. So let's get underway. Just to give you an idea of what we'll be talking about through the next 45 minutes or so, I'll give you an overview of the workflow, talk about data selection and QC for building faulted grids, a very quick review of gridding fundamentals, and then we'll step through an example workflow. Obviously, in the course, we'll have 4 days to work through a lot of examples. We'll try different algorithms. We'll experiment with things that people don't always have a chance to do in their everyday work. Sometimes people are so focused on just getting out a map, you don't take the time up front to make sure you've got the data completely organized and decide what are the best ways to attack the entire project. We'll look at how to QC faulted surfaces once you've built your grids, how to estimate some isocores from faulted surfaces, and then as we have time at the end, we'll talk about some tips for documentation and making presentations. So the mapping workflow in Petrel, it sounds like a lot of you have already had some experience with Petrel. So the key thing about any workflow is that it is iterative. In fact, if you think about it, it's the 3 I's. You integrate your data, you interpret your data, and then you iterate back through it. A project is never really done. Every time you get a new well pick or some reprocessed seismic, you're going to be rebuilding pretty much the entire project. So you need to begin with that thought process. So the fundamental thing you should do at the beginning of every project is think about what is the object of the exercise? What is your deliverable? And then think about how are you going to update that and build a very solid workflow that you can reproduce or that someone else can reproduce. Fields will live for 15 to 30 years or more, and I hope that you don't spend your entire career on a single project. You're going to be handing off to other people. So an emphasis on the course is how to document your work using the automated workflows in Petrel, as well as how to build sensible reports that other people can follow later on. So the faulted surface workflow is a little bit different. We'll be talking about that today. Again, you need to start with your basic well data. You need to look for fault cuts in your wells. You need to interpret your faults and horizons from whatever seismic you have. Grid preliminary faults and surfaces. Take a look at what your data are trying to tell you and identify problems early on. This is a good time to look at your seismic data, whether it's 2D or 3D. Look at how the lines tie and how well your wells tie. It's become very common with depth-based seismic volumes to build velocity models with only a small subset of the wells. And once you start trying to match those depth horizon interpretations to your well tops, you'll find that there may be some significant errors. If you feed those back in a timely fashion to the people doing your geophysical processing, you may be able to update your velocity grids and get a much better solution from point forward. At some point, you're going to have to construct fault polygons because in Petrel's 2D surface mapping world, fault polygons are what you use. If you go on to building 3D faulted grids, you can use fault sticks or fault surfaces directly. But in the 2D mapping world, you have to use the fault sticks and the fault surfaces to construct fault polygons. And we'll walk through how you do that. Then you incorporate all of that information to create fault surfaces and start estimating your isocores. And always, always, always QC all of the surfaces, all of the fault offsets, look at your isocores critically, and make sure everything ties back to your well picks. And build in plenty of time to modify and update your grids. It's something that people leave themselves short of time. Sometimes that's unavoidable. Your geophysicist may be interpreting on a newly reprocessed volume. So you're just going to have to push through it and make sure that everything ties and is suitable to handing on to, for example, your reservoir engineer. They always complain that geoscientists never give them enough time, and I have to confess that they're usually right. And also, make sure that you've got a good process in place for documenting your results. Okay, mapping your surfaces and key components. The first thing is always data selection and preparation. In the course, we spend a significant amount of time talking about how to make sure that you have all of the data you need and that it is suitable for the type of map that you're trying to build. It's very common for wells to have missing tops, for missing wells to happen, or in some cases, if you have multiple interpreters on a project, you'll have duplicate tops, and it's your decision as to which set of tops to use in a particular map. You need to define on the grid area and geometry what gridding algorithms and parameters are appropriate. And then again, you'll hear this from me continually, grid quality checking and modification. So the key components for mapping faulted surfaces are a little bit different. You need to bear in mind always that the fault displacements should be consistent. And that's both along a fault and for each faulted horizon that you may have in stacked sequence. An exception to that, of course, is strike slip or wrench faults, where you may, in fact, you will usually have inconsistent looking fault displacements along the fault. Also, the structural form of the surface should generally be consistent on each side of the fault. Exceptions may be syndepositional faults or growth faults or strike slip faults. So how do you select and prepare your fault data? Well, first, decide what data sources you have. If you see fault cuts in wells, you're looking for missing or repeat sections. That may be expressed in terms of logs, where you may identify missing or repeat section. You may see anomalies on cross sections, or you may be fortunate enough to have paleo samples that will flag those missing or repeat sections. Use every piece of data that you have available. On your seismic interpretation, whether, well, on 2D and 3D data, you'll have fault sticks and planes from your vertical sections. If you have 3D data, you may also create time or depth slices or horizon slices, depending on your software, or you may be able to generate some ant tracks. I've had mixed success with those. Sometimes they work really well. Other times you end up with a lot of false positives, is how I'd put it. From those, you can get fault polygons and fault centerlines. You can also infer whether you have faults or not based on maps. If you can see abrupt changes in depth or thickness, curvature, for example, abrupt changes in dip, or abrupt changes in seismic attributes. On the right side here, you see a map that started as a depth map, but I used the edge detection surface attribute that's available in Petrel to highlight where faults might exist. What it does is it looks for those rapid changes in depth, and it highlights those in a bright color. Similar to ant tracks, I find that you will frequently get some false positives. Not all of these little trends are probably real faults, but it also gives you an early look at what areas may be most structurally complex so you can start thinking about how to attack different parts of your mapped region. If you do have fault cuts and wells, those are really hard data, and you have to plan on honoring those. The fault cuts and wells will give you not just the depth of where the fault cuts the well, but it will also help you define the amount of missing and repeat section that you need to honor in your final faulted grids. A side note when you're interpreting seismic, whether 2D or 3D, if you're working in a depth volume, it's very common for people to be interpreting at a very high degree of vertical exaggeration, 3 or 5, or I've seen as high as 20 times vertical exaggeration in some unconventional plays. And what that does is it really distorts the shape and angle of the faults that you're interpreting. For example, if you're working in an extensional regime, you would expect the faults to be high angle, typically 50 to 70 degrees or more. But if you have interpreted that on a seismic section that has a vertical exaggeration of 3, like you see here, and then you compress that to a 1-to-1 vertical exaggeration, you see that the fault dips are more like 25 or 30 degrees. Now, bearing in mind that this is very poor quality seismic, and frankly, I did not do the interpretation, you would start questioning maybe these faults have been rotated later, or maybe you have picked them to be representative of a structural setting that is not the correct one. So always, it's a really quick thing to do in your workstations. Just drop your vertical exaggeration down to 1. It will give you a very different look at your structural setting. Another thing to bear in mind as you're doing the interpretation, particularly if you have 3D auto picking turned on, is be careful around the areas of faults. First, you should always set your main framework faults as opaque barriers. Some software allows that, some does not. But if you set those up as opaque barriers, you may still end up with the auto picking wrapping around the fault and giving you inconsistent interpreted horizons that in areas that should be in the fault gap. What I do then is clean out that gap, blank out any of those interpreted points that are inconsistent, and regrid the surface. That gives you a better look at all of your horizons, and it just cleans up those faults so you can move on to calculating better center lines and better fault polygons. As an example, let me see if I can get this video to turn on. To clean out fault gaps, what I like to do is set up a 2D window on one side, a 3D window on the other, automate cursor tracking, so the cursor here and here are in the same locations, and then start with your delete option, just cleaning out all of the inconsistent points. And that's active on either the 3D or on the 2D side. The 2D gives you a good overhead look, but on the 3D, you may see additional areas adjacent to the fault that also need to be cleaned out. Typically, the downthrown side of a fault is going to be a bit more disturbed than the upper side. So if you clean out some of these points, when you regrid the surface, you're going to get a cleaner, better defined, better behaved surface to work with. So these are the kinds of exercises that we will do in the course. And since we'll be working on, I would say, moderately poor quality seismic data, it is probably more representative of the kind of work you'll be facing in your everyday work. I've found that if you have a demo set for teaching that's too perfect, when you get back to your own project, it's not as easy to work with. So when you've got seismic interpretation, like I said, the first thing to do is identify your main framework faults. Start checking those for consistency. For example, I'll try to zoom into an area here. You've got some fault sticks that are at a different angle than some of the others. You've got 3 fault sticks here when it looks like that fault really extends much farther. And if you look at the fault back here, these fault sticks are going in different directions. You've got some odd ones at the end. And when you grid those to create fault surfaces, you're going to get fault surfaces that are just not well behaved. I also like to assign meaningful names to the faults. Just naming the fault orange or blue is not terribly helpful, especially if you pass the project on to someone else. I like sorting faults by type, and this is in your input panel, so you can create separate subfolders for each group of faults. One of the techniques that I've seen used is to use color to represent different dip directions. When you display those, it can give you some really good ideas about the structural growth and history just by the color coding. You may sort them by dip direction, relative age, whether they're major or minor, whether they're synthetic or anesthetic. And it's a very good idea, particularly if you're going on to 3D faulted gridding, to identify the faults that are lambdas or Y types, because those will require a lot of special handling in 3D grids. So what to do with fault sticks? I mentioned that faults have to be consistent, and the best way to accomplish that is to have fault sticks themselves that are consistent, similar in height or smoothly varying, similar in shape. And if you've interpreted horizontal fault sticks, for example, from a horizontal slice or a time or depth slice, make sure that they don't extend past your vertical fault sticks. Otherwise, your calculated fault grid will not be well behaved. You need to get them spaced closely enough to represent the shape of the fault, and particularly as you get close to fault intersections, you need to have those pretty closely spaced too. Once you've gridded fault plane surfaces, or if your software creates fault surfaces automatically, you need to look at those very critically. You need to look for unusual curvature. You need to look for areas where a fault has been continued when it really doesn't make geologic sense. For example, in this area, these fault sticks are the same color and it looks like they represent one fault. But given the angle that this fault takes here, and that you have very different heights of these sticks, and that when you calculate a fault surface from them, you get this strange curvature, it's not reasonable to expect that this really is one fault. So what you can do in editing is you can identify these fault sticks, extract them, and create a separate fault that then you can intersect with this major one. So fault center lines are probably not going to be used directly when you create faulted surfaces, but they're a good first step for one thing to identify the approximate average intersection between a fault and a structural surface. And you can use them after editing to create fault polygons. But often they require so much editing. For example, this fault center line, you can see it just takes all sorts of odd turns because the intersection isn't clean. If it takes so much editing to do that, it's probably easiest to manually create fault polygons, as we'll show in the course. The other thing to bear in mind is that fault center lines and fault polygons for adjacent horizons need to stack consistently. Unless a fault has been deformed by a later structural event to create a recurved fault. But always bear in mind the fault geometries like they teach in the subsurface mapping course. Understand the structural regime, understand what the faults should look like, and then make sure that the faults that you build in the workstation actually represent that. Another place to get good fault center lines, or at least fault traces, is from your horizon slices or time depth slices. You can also identify areas that look more structurally complex and start picking out faults that you may want to rethink. For example, this purplish fault that wanders across, it changes orientation, it changes strike, and it cuts across another major fault in a pattern that just doesn't look terribly geologic. You also have a fault here that's identified, but it cuts across all of the other trends. So that's one that I would go back and look at the interpretation and think about whether it's realistic or if maybe it should be actually truncating against this yellow fault here. One of the interpretation tips is if you have faults that really do cross in an X like this, your gridding will behave better if you actually split those into separate faults at the crossing point and offset the intersection slightly. And that's a particular problem if you go into the three-dimensional gridding. In that case, you're going to have to split those X faults. So you may as well get it done as you're building your 2D surfaces to go into the 3D gridding. So fault polygons, you can digitize them manually, and often that's the easiest way to do it. If your fault center lines are particularly clean and good, you can copy the center line to the up-thrown side of the fault, to the down-thrown side of the fault, and then append those and make closed polygons from them. Usually, however, you're going to end up digitizing the fault polygons directly on your depth surfaces. Allow plenty of time, because your first go, you can see some of these fault polygons just don't look terribly consistent. And so as part of your QC process, I'll show that you're going to regrid fault surfaces from the fault polygons you create, and then compare those back to any seismic interpretations you have, or look for unusual features. As part of the fault polygon building process, you should name the fault polygons to correspond to the surface and the fault name. And again, fault polygons for adjacent horizons should stack consistently. I've shown an example over here that you can create a surface edge based on a surface that has fault gaps, and that will create a single polygon set around each of those fault gaps. It's good for visualization, but I find that, again, editing an image like this and a set of polygons like this, it takes so much work that it's really easier to use your own interpretation and judgment to digitize the fault polygons manually. So a quick review of gridding fundamentals. I really like gridding fundamentals. It's something that I've spent a lot of time on. I've actually written some computer code for gridding. So I've definitely gotten down way deeper than most people ever care to. But there are certain fundamentals that you don't need to think about the math at all. You just need to think about, what are you trying to accomplish with your maps? A major fail that I've seen frequently is not getting your initial grid large enough. You should always confer with your reservoir engineers to understand where their contacts are. If you're in a development or a production project, talk to your geophysicist to see if there are any hydrocarbon indicators, or if you can see indications of a gas oil or a gas water contact, and make sure that your grids get large enough to include those contact zones. If you're working with multiple surface, Petrel is not particularly strict on this, but I have found that it's good practice to use the same grid definition for all of the surfaces. A handy hint is that you can save a lot of grid cells just by orienting the grid parallel to a dominant structural or stratigraphic feature. Grids do not all have to be oriented north-south, east-west. When you get to determining a cell size, your cell needs to be small enough to represent your smallest feature of interest. And you should definitely strive to have no more than one control point per cell. Sometimes that's unavoidable if you're working with a very large regional project, but no algorithm is going to be able to satisfy and match multiple control points in a single cell. Again, if you go to 3D gridding, it behaves a little better, but the 2D algorithms are not quite as powerful. In your total cell count, the reason you need to think about this is if you have a lower quality video card, or if you don't have enough system RAM, as you get to very large cell counts and you're dealing with multiple horizons, you may experience system slowdowns, visualization problems. You may even crash. So how do you decide on what is the right resolution? On the left here, I've got a high resolution grid that was based from 3D Seismic. And personally, I don't think it's a very good map. I would not use this certainly in presentations. But this small area is blown up over here on the right with different grid cell sizes. So at a 40 by 40 foot cell, and I apologize to our international users, this is a US based system. So think of it maybe 12 by 12 meters. You would end up with over 12 million cells. If you switch to 200 by 200 foot cells, you've cut that to fewer than 500,000 cells for a single surface. And if you go even more, 500 by 500 cells, you're under 100,000 cell total. But you can see the effect on the quality of the contours. On the left, you've imaged that very detailed seismic interpretation really well. As you get to a slightly larger cell, you've created a slight closed flow here. And as you move to the coarser grid cell size, you've lost a lot of the resolution on that contour. So you have to determine what is the cell size you need and what problems that may give you as far as your visualization and system RAM goes. Once you've decided on the grid geometry, your next major decision is selecting a grid algorithm. And this is where people will argue interminably. Petrel actually gives you some good tools, like you tell it what kind of data you have, and it will suggest an algorithm for that. Unfortunately, it doesn't change the parameters that it uses for defaults once it's made those recommendations. So even after you've selected an algorithm, parameter selection is extremely important. So some algorithms are appropriate for data types and some algorithms are not. What you can be sure of is that depending on the algorithm, you're going to get a slightly different or a very different looking map. The convergent interpolation gridding algorithm is the one that's chosen as the default most often, and there are some really good reasons for that. One difference you'll see between convergent and minimum curvature, in the area where you've got good well control, the final maps look pretty similar. The differences come at edge effects. Minimum curvature is known for introducing some pretty strong edge effects as you get away from your control points. And generally that's not a significant problem. But if you're working with reserve calculations, you need to be extremely careful not to exceed, for example, maximum isochord thicknesses, maximum height of a structure. So for a lot of reasons, convergent interpolation is probably the first algorithm you should look at. But all of these algorithms are included for reasons. There are some very good reasons to look at using the moving average algorithm. Kriging is a wonderful algorithm for certain things. Personally, I've never used the cosine expansion algorithm when I have a choice, but there may be particular projects where you work with that algorithm and it's well suited to your data type and the objective. It's worth getting familiar with all of the tools that are available in each algorithm. For example, convergent interpolation, it accepts not only your fault centerlines and polygons, but you can include additional control points. You can include a trend surface, which will help shape the surface away from your control points. And one thing I really like about it is that it will include dip and azimuth. So for example, all of these algorithms will match your data points. But if you also have dip and strike as data that's associated with a particular formation top, when you use this algorithm and include dip and azimuth, the surface will honor not only the well's depth, but its dip and direction of dip. And in certain structural settings, that can be extremely valuable. So the minimum curvature, again, it will include fault centerlines and polygons. And really the only difference in the checklist is that it will not include dip and azimuth. Interestingly, isochord maps, the isochord algorithm will let you drop in fault centerlines and polygons. Use that with care, because typically an isochord or a post-depositional structure, you shouldn't see thickness across a fault. So using fault polygons and centerlines with isochords needs some careful consideration first. So the convergent interpolation algorithm, it's definitely worth reading the Petrel manual on this. The Petrel guides have gotten pretty good over the last few years, and the section on the convergent interpolation algorithm is particularly worth reading. One reason to use it is it's extremely efficient. Some algorithms take a very long time to get to a result. One reason it's efficient is that it starts with a very coarse grid, and then it refines that grid sequentially by a factor of 2 until it gets to a surface that is acceptable and that it ties the control points. The reason that people like to use it with faults is that you can include the fault polygons from the very beginning of the algorithm, or you can preserve the surface structure pre-fault a bit better by bringing the fault polygons only later in the process. Of course, the fault polygons are always integrated into the last step to preserve the offset. So we've worked through the basics. Now let's take a look at an example workflow. Time check, we're doing okay. So the faulted surface workflow, as you grid preliminary faults and surfaces, then you'll resolve your line and will miss ties, build the fault polygons, and as we've discussed, work all the way through, integrating, interpreting, and then iterating again. So the first thing that I always do when I've got a set of input data is I start visualizing everything. It's also a good time to start organizing your input panel. Use folders, use subfolders, use the favorites panel, especially in large projects where you've got hundreds of wells, maybe a dozen or more surfaces and lots of faults. You can spend a lot of time just trying to find a particular data object. If you use the favorites panel, you work with just the objects that you're dealing with at the moment. And you can drop things in and out of the favorites panel. It's pretty easy to do, and I think it's definitely an underused feature of Petrel. The next thing I do is I build quick look surfaces without faults. This gives me a good idea of if I've got any data busts, if my grid size is extensive enough, how many grid cells I'm going to have. And by the way, if you're not building elevation maps from your well KBs, particularly if you're working onshore, you're probably missing an opportunity to find data problems very early in your mapping process. It's particularly a problem if you're working in unconventionals where your structures are quite flat and a small difference in elevation may cause you to actually miss your mapping target. So in the course, we actually show some examples of that and talk about how to resolve them. So in your workflow, you look at your fault plane surfaces and make sure that they're exactly what you want to work with. As we talked about earlier, you can decide to split particular faults. You may have two faults that should be joined. Quite often, you'll be able to truncate one fault against another by using a surface operation. And this is another opportunity to make sure that your faults extend vertically through all of the horizons that you intend to map. So after you've truncated the fault surfaces, you've maybe truncated them vertically as well for better visualization. You can look again, and over here I see that this gray fault does not fully intersect this pink one. You may want to fix that right here, or you may want to connect them using fault polygons later. Partly it depends on if you're moving into the 3D gridding world, in which case you're going to have to connect those fault surfaces anyway. You may also choose not to include some of the small or inconsistent faults that were interpreted on Seismic, but have no bearing or relevance to your particular project. Also, I like to create a Petrel folder with just the fault set that I'm using for a particular set of maps. Again, organization will save you so much time, and when you do document the project and hand it off to someone else, they won't have to go through sometimes literally hundreds of preliminary maps to figure out what you were actually trying to say. So when you create the fault center lines, that's actually done with another surface operation where you create an intersection between your interpreted horizon and the fault surfaces. And then you look at those and you say, oh man, that is really not what I had in mind. At that point, you can choose to edit them, or you can move on and start digitizing each polygon manually. One of the advantages with digitizing polygons on a depth surface, you can do it on a time surface as well, but typically doing it on a depth surface is more effective because as you digitize each polygon point, you can assign the Z value of that depth surface automatically. And what that does for you is when you display it in 3D, you can make sure that the fault polygon actually wraps around the fault. Here, maybe these fault polygon points aren't sufficiently far away, so you can move those in either 3D or in 2D. The thing is, once you move one of these polygon points, you have to reattach it to that depth surface. You also need to make sure that your fault polygon points are sampled densely enough to match the shape of the fault. Sometimes what I'll do is just digitize the up-thrown side and then copy and paste that to the down-thrown side and then connect the two polygons to create a closed polygon. Whatever works for you. One thing that you do have to make sure of, as I've mentioned earlier, is that the polygons stack in a structurally consistent way. So if you have a fault set of polygons on your shallow, and then you add polygons to your middle horizon, and then to your deep horizon, they should follow the dip and the offset direction of that shallow fault. Otherwise, when you try to grid the surfaces and then look at isocores, you're going to get very strange results that are just not geologically or geometrically possible. A final QC, once you've got your fault polygons constructed, is to actually try to make fault surfaces from them and then compare those fault surfaces that you've calculated to your original seismic interpretations. This fault looks reasonably good. This fault looks reasonably good. This fault has an odd bulge that clearly does not look geologic. So I'd go back, I'd look at my interpretations, I'd modify the fault polygons, recalculate the fault surface, and then I'd be ready to use these fault polygons in my gridding. So at that point, you've got all of these individual fault polygons. What you need to do is append them all into a single fault polygon set because the convergent interpolation algorithm only accepts a single fault polygon object. This is also a good chance to make sure that your intersections are fully connected and then redisplay those on your 3D and make sure that everything is still fit. It's also an opportunity to experiment with some different structural interpretations. For example, what if this small fault here doesn't actually truncate this other longer fault? What if instead it's open and you've got a potential relay ramp or migration path here? So you can create different versions of your fault polygon sets to test those different structural interpretations. When you get into gridding the faulted surfaces, your fault polygon parameters for the convergent gridding algorithm here, this is where you choose when to integrate the fault polygons into the algorithm. As I mentioned earlier, this influence percent controls whether you integrate the fault polygons through the entire process or only in the later iterations. The default is 100%, and usually that's appropriate. Honestly, I've never seen a huge difference, but it's certainly worth experimenting with. Just try it out. This option to use the Z values, if you have attached your fault polygons to the depths, you can use those as additional control points in the gridding algorithm. The fill inside controls whether the surface actually extrapolates across the fault gaps or leaves those fault gaps as nulls. The default is to fill inside, and that's usually a good choice because on your maps you can always fill the fault polygons to hide where you would have fault gaps. So how do you identify displacement problems? The faulted grid QC is going to take a lot more time than checking quality for unfaulted grids. So the things you need to really look for are consistent displacements, whether the fault reverses, turning into scissor or screw faults. And that problem will be most common where you've got low throw faults, the little ones, at fault intersections and near the tip points. And as mentioned, it's always a good idea to compare your gridded surfaces, whether horizons or faults, to your interpreted seismic. Something I really like as a feature is to create an intersection player so you can look at the stacked surfaces and check that your fault offsets and your horizon thicknesses are consistent. Now, admittedly, I only have 3 interpreted faults here, and from your offsets, it's pretty clear that you should have additional faults here. But if you click through this and it plays, you can set up the intersection player and you can see it here moving through the section. So the fault offsets look mostly reasonable, except in certain places you've got the horizon turning up too much. And this easternmost fault has an odd profile where you'd want to go back in, look at that, and if it's relevant to your prospect or project, you'd want to clean those up. But at least you have a quick method to identify where your problems are, and then you can attack them. Some of the other QC tools, you have to validate that the fault offsets are additive. This is one of the themes of the subsurface mapping course, and I've carried that into the Petrel course as well. For example, here you've got 2 small faults, about 60 meters offset, about 80 meters offset. Those should add up to about 140 meters offset once they merge. If they do not, then you need to reconsider how you've mapped in those faults and get them geometrically plausible. The way you measure this in the 2D world is with the distance measuring tool. In the 3D world, you have the Rock Deformation Research Toolkit, which is extremely powerful, and you can actually map fault offsets, you can map transmissivities, and you can even look at things like shale gouge ratios. So there are a lot of reasons to look at faults in the 3-dimensional gridding world, but it is a much more complicated process. So I can understand that if you don't need to, staying with the 2D surface mapping is perfectly reasonable. Now, when you're getting into isocores in a faulted surface, obviously when you're in the area of the fault gaps or the fault influence, your isocores are not going to be valid. Here you've got a faulted isocore draped over a structural surface, and you can see where the isocore goes to 0. Now, often you need to just get a quick estimate of what an isocore would look like if you took the influence of the faults out. And that's actually pretty easy to do by constructing some blanking areas. You just take your fault polygons, expand them out, blank in the regions, and then interpolate or extrapolate across those gaps. So the way you do that, you use some polygon operations and some surface operations. You eliminate inside, you create a null, and then you use another surface operation to simply extrapolate across. Obviously, it's not perfect, but it's much better than in the areas that you know faults exist where you haven't done that process. So it's an estimation, but it can often be good enough. I'll tell you what, we're getting close to the time to end. Let me just touch very quickly on documenting procedures. I always leave PowerPoint open. There's another good piece of software called Snagit that is very good for capturing screenshots, even some video. Document every piece of data that you've used. Identify the data that you did not use. For example, small faults or wells that exist in the area but maybe did not penetrate the mapped horizons. If you have standard reporting formats or templates, use that as you work through the project. Don't wait until the end to try to remember what you did and why. Also, it's really important to keep clean projects. Delete out-of-date projects. If you really want to hold on to those, just create a new copy of the project. clean out the new copy. It's always a good idea to do that at specific milestones and use only the relevant data and the work products. If you're working in a production environment where you have to document reserves, lock that project down and make sure that it's very well documented, so if you are audited eventually, people can reproduce your maps exactly. Use your workflows as internal project documentation. You can regenerate surfaces, but it's much more reliable if you've actually created a workflow showing the input data that you used, all of the parameters, all of the specific gridding choices that you made, and include any grid operations that you did. And always, always, always build a standard process for updating your corporate data stores. A lot of people are using Studio, for example, or reference projects. Some companies are using OpenWorks as a data repository. But it's very important, if you have updated information, if you've created new well tops, edited information, have a process to feed that back to your corporate data store. So people working in the same area will know exactly what current interpretation is. We'll spend some time in the course on building map templates. It's very important to have all of your maps have a common look and feel. I like to build different templates for different display sizes, so I can build things that are appropriate for PowerPoint, as well as the wall size displays that people like to see in meetings. Auto text is something that will let you populate headers and info boxes very easily, and it's a very good idea to document a project name. You can even document where a project is stored on a hard drive or a server. And I always like to make people sign their work, so I always include a signature box. So an example of some simple map templates, including log signatures, which we'll also show you how to build during the course. Keep similar contouring styles, contour increments, color bars if you can. Include all of the map elements like north arrows, scale bars, and all of these things can be preset, so you don't have to spend a lot of time building each map individually. It's kind of set it and forget it. So to review what we've done is I showed you an overview of the mapping workflow and a slight variation on that for faulted surfaces, how to select and QC your data, a very light touch on gridding fundamentals, an example workflow, how to QC your fault surfaces, estimating isocores from faulted surfaces, some documentation tips, and some presentation tips. And now we'll open it up for questions if you have any. I hope
Great,
you found
thanks, Lori. I want to remind our listeners today that you are muted, so you need to post your questions in the question box in the GoToWebinar feature. Later today, you'll receive a link to the recording of today's webinar and evaluation form, and we'll provide you with details on setting up an in-house class on the principles of mapping with Petrel with Lori Green. So it looks like we're starting to get some questions now. So Lori, would these techniques work with reverse faults?
You'd have to modify them somewhat. Certainly some of the data preparation would work, but when you're creating fault polygons for reverse faults, you're going to end up having to create the surfaces in segments because the 2D mapping does not really work well with multi-Z surfaces. Now, if you're using Petrel's structural framework application, that you may have some success with. I've had mixed success using the structural framework process. When it works, it's brilliant. I tend to favor showing people some of the fundamentals. So when the automated processes don't work, you can get in and manage them by hand. But yes, for reverse faults, you're going to have to grid your surfaces in pieces.
So what does one do if you don't have 3D seismic?
You work with what you've got. Certain areas, I mean, Often you will have 2D seismic. The only exception I can think of is if you're working in a very old area where you've mostly got, for example, an unconventional play with hundreds of wells already, and maybe just some very sparse 2D. But if you do have 2D seismic, you can certainly use it for getting fault sticks and maybe even projecting through some fault surfaces. But you will probably have to do a lot more work in shaping your fault surfaces before you can use them to create fault centerlines and fault polygons.
So next question, would it be possible to highlight more about selecting the right gridding in addition to data density?
Yeah, I mean, it all comes back to an optimization exercise. If you're working in an area where you've got very little control, you're going to need a finer cell size. If you're working in something like Michigan where you've got pinnacle reefs, you're going to have a very small cell size. But the smaller cell size you get, the more cells you're going to have. And that's usually not as big a problem if you're working with 2D surfaces. But if you move into the 3D gridding, it aggravates it because you're looking at the number of vertical cells as well. So understand what it is you're trying to image. How tight a focus do you need? And that will tell you the size cell you want to have. And then you have to look at your hardware and firmware and see what you can manage. It's always a balancing act. One thing I'll say is that you can start with a very coarse grid, for example, if you're looking at a regional project, and have those with large cells. And then if you need to extract a piece of that, Petrel makes that very easy to do. And then you can regrid that subset with a much finer cell size. And eventually you can resample that back into the coarser grid. That's a really good approach. For example, working regional Gulf of Mexico and then narrowing it down to a specific field.
Here's another gridding question. Is there any rule of thumb for choosing the resolution of the grid?
It goes back to how small a feature do you need. The smallest cell size I've ever seen used was a 10 by 10 foot, so say 3 by 3 meter cell, where the engineer was trying to get a very good idea of which cells were contributing to production in a very long horizontal well. But that was for a very specific purpose. I mean, typically you're looking at 50 by 50 foot or up to 200 by 200 foot cells for a typical mapping exercise. One other thing to consider if you're working in a faulted terrain is if you have small fault compartments, a coarse grid cell size is not going to give you a solution for a surface in that small fault compartment. So to visualize faults well, as far as curvature and making sure that the fault compartments actually have a surface calculated for them, then again, you need to go to a finer cell size. That's why I say experiment. To create 2D surfaces is really quick, and just experiment with different cell sizes and see if that will accomplish your objective. Even in an exploration terrain, I like to talk with the reservoir engineers and figure out what they're going to do with my maps and let that be my guide. The reservoir engineers are often the consumer of everything we geoscientists do, so it's good to get them involved early in the process. Also, if you have people doing basin modeling, they may need a much larger area and they can handle much coarser grid cells because their objective is somewhat different. Work as a team.
Always a good idea. The next question, my seismic data is in the time domain. Can I still use it?
Yes. The nice thing about fault polygons and fault centerlines is that they're essentially dimensionless. Now, what that means is they will be in the right location in terms of X, Y. They're not going to be in the right location in terms of depth or time. But you can still use the fault polygons and the gridding algorithms, recognize those as a barrier, but it can't use the associated Z values to calculate, for example, fault throw. but yes, you can definitely use those. I like interpreting in time anyway because it just had less done to it.
Thank you. I want to remind the listeners that Laurie will be back on June 27th for a second webinar featuring mapping horizontal wells with Petrel. And after today's webinar is over, you'll receive a link to a recording and evaluation form. We'd love to get your feedback, and we'll give you details on how to set up an in-house course in your company on principles of mapping with Petrel with Laurie Green. Thank you, Laurie. Thanks, everybody. Goodbye.
Thank you.